Section 7.2 Volume the disk method. There are three objectives: to find the volume of a solid of revolution using the disk method, to find the volume of a solid of revolution using the washer method, and finally to find the volume of a solid with known cross sections. Example 1 will be an example with the disk method. The region between the graph of f of x equals 2 plus x cosine x and the x-axis over the interval -2, 2 is revolved about the x-axis to generate a solid. Find the volume of the solid using your GDC. This is the graph, and before we solve this problem, we'll see a little animation to explain what the disk method actually is. So this is an animation that's going to show us volumes of revolution. Here we have one rectangle, and we're going to see what happens to that rectangle when we rotate about the x-axis. So as it rotates about the x-axis, it creates a cylinder. The volume of that cylinder is pi r squared times h, pi times r squared times h, and in this case h is this. So what is r? R is actually f of x. The radius of the cylinder is defined by the height of the function at that given point. If we break down the interval AB into 5 subintervals, for example, we will have 5 cylinders like this, one next to the other, and by adding up all these volumes, the volume of these 5 cylinders, we will find the area under the curve. In the case here, where the cylinders have a certain height, we will find an approximation, exactly like we used to find approximations for areas with Riemann sum. In this case specifically, we are actually using RRAM because we chose the right endpoint to define the height of the rectangle. And adding these, we can find an estimation of the volume. Now, if instead of just having 5 cylinders, we actually have infinitely many, the height of these cylinders will become infinitely small. We will write it dx, and we'll have an integral instead of just a sum of 5 objects. So let's see what it looks like when we actually using infinitely thin rectangles. If we revolve, we will have a volume of revolution that looks like this, and we will add all these disks, hence the name disk method. So all these disks together create a volume. Now notice how I've rotated about the x-axis. In some exercises it's not going to be rotated about the x-axis but about another value, for example x equals -1. If we revolve this blue area about the new axis of revolution, it also creates a volume which has a hole in the middle. Just for a little moment, let's ignore the hole in the middle. How are we going to find the radius of that disk? The radius of the disk is not going to be f of x, it's going to be f of x plus 1. Plus 1 because I moved the axis to y equals -1. So the radius of each of these disks is actually f of x plus 1. So the formula would become pi times open parenthesis f of x plus 1 close parenthesis squared. We can also rotate above. Let's see. So if we rotate above, we also find a volume like this. So let's go back to the notes now. we will revolve this region about the x-axis and we will obtain a volume like this. So we can see our disk here, and the area of the disk is pi r squared, which is in fact pi times f of x squared. So when we want to find the volume of this object, we will integrate from x equals -2 to x equals 2 of the area times dx. I haven't written it here, it's written later on. This is the area times dx. In this example, f of x is 2 plus x cosine x, so I can just substitute. The volume equals the integral from -2 to 2 of pi times 2 plus x cosine x squared dx. And if we use our calculator, we find the answer 52.429. Example 2 is washers. So with washers, what we do is we actually integrate with disks, and then we subtract other disks inside to kind of create a hole in the middle. The region in the first quadrant enclosed by the y-axis and the graphs of f of x equals cosine x and g of x equals sine x is revolved about the x-axis to form a solid. Find its volume by hand. Here are the two graphs, y equals sine x, y equals cosine x. The region that is defined in this exercise is in the first quadrant, and it's enclosed by three things: the y-axis, this graph, and this graph. So we are talking about that region here in red. If we revolve this region about the x-axis, we get a volume that kind of looks like that. So it rotated, and here there's kind of a hole. It's like a cone that has been removed from the volume. To find this volume, what we do is we actually find the volume of this entire block, and then we subtract the volume of this cone-like shape inside. The volume of the entire block is the integral from 0 to pi over 4 of a times dx, so a being pi r squared, pi times f of x squared, and f of x is in this case cosine x because we are studying the function that is above. So the function above is here, it's cosine x. So each disk has an area of pi r squared, which is pi times cosine squared x. And when we integrate that, we'll have the volume of the entire block. Now we need to subtract the volume of this cone-like shape. It's not a straight cone, but it's almost a cone here. And this is also found by using the disk method. So the washer method is really taking a disk and subtracting a disk in the middle, a smaller disk in the middle. And for this cone-like shape, the area is also pi r squared, but this time the radius is defined by the function g of x, so sine x. And therefore, it's the integral from 0 to pi over 4 of pi times sine of x squared dx. I didn't make any comment about the endpoints. We are integrating from x equals 0 because we are bounded by the y-axis, and this upper bound is pi over 4 because this is the x value of the intersection of the two graphs. Here, this point is at x equals pi over 4. Just like when we were finding the area between two curves, it's easier at the beginning to see this as one volume minus a second volume that is smaller. But obviously, you can also write this as one integral. It's the integral from 0 to pi over 4 of pi times cosine squared minus sine squared dx. Huge warning here. it is not the same as the integral of pi times cosine x minus sine x squared. That's a huge mistake that shows up all the time, so I'm really trying to warn you. It's f squared of x minus g squared of x. It is not f minus g and you square the difference. So let's remove this and solve. There's a trick here. Cosine squared x minus sine squared x is actually cosine of 2x, if you remember from pre-calc. We studied double angle identities, and that is a much easier integral to find by hand. The integral of cosine of 2x dx is 1/2 sine of 2x. So after we've plugged in x equals pi over 4 and x equals 0, we can finally find that the answer is that the volume is pi over 2. Riemann sums. So it's going to use the same techniques as what we've seen with disks, but we are estimating volumes. So typically it's going to be used when we have tables of values or when we don't know how to integrate the function. The question is, estimate the volume of a sphere generated by revolving the graph of f of x equals root 25 minus x squared about the x-axis. Estimate the volume V of the sphere by partitioning the interval -5, 5 into 5 subintervals of equal length and using MRAM. Here's the graph. If we partition it into 5 subintervals, they're going to look like that. -5, -3, -1, 1, 3, 5. And since we use MRAM, we're going to look for the midpoint of each of these subintervals. So it's going to be -4, here -2, here 0, here 2, and 4. These are the values of x that are going to be used to define the height of the rectangles. The rectangles look like that. So x equals -4 defines the height of the rectangle. X equals -2, this rectangle. X equals 0, this rectangle. X equals 2 here. And finally x equals 4. So let's look at each of these rectangles and see what happens when they are rotated about the x-axis. Each rectangle revolved about the x-axis becomes a cylinder, like this. What is the volume of these cylinders? It's base times height, so the base is the surface of the disk, it's pi r squared, times the height here being this. So the height is 2 because this interval has subintervals of length 2. 2, 2, 2, 2, 2. Volume of a cylinder, pi r squared times h. Now we just need to make a table. We list the midpoints. For each of these midpoints we can find the radius of the cylinder. So the radius is defined by actually f of x, f of the midpoint. So f of -4, if we plug it into our equation, we find f of -4 equals 3. And by using the formula, the volume of this cylinder is pi times 3 squared times 2, pi times r squared times h, and we find that the volume of the first cylinder is 18 pi. The first cylinder is the cylinder we would find when we would rotate this rectangle. We just need to repeat this 4 more times for each of the other midpoints, and this is what we get. So once we're done with that, we can add up the 5 cylinders to find the total volume that we estimate for the sphere. Total 170 pi, which is approximately 534.071. So that's the end of this exercise. Just as an extra point, we could want to compare this to the real volume of the sphere, and to find the volume of a sphere, it's obviously 4 over 3 pi r cubed. The true volume is 523.6, so our estimate is really not bad. The volume of a solid of known integrable cross-section area A of x from A to B is the integral of A from A to B. This is the formula that we actually can use not just for cross-sections but also for disks. Pi r squared is the area of a disk times dx. dx is the thickness of that disk. It's infinitely narrow, but then we sum infinitely many of these disks. So we'll see a second animation now to explain what cross-sections are. We're going to see two examples of cross-sections now. Here we have a function f of x equals, and it's r, the square root of r squared minus x squared. And if we want to create cross-sections here, we're going to try to see it in 3D. So we drop the y-axis like that, and let's imagine now that for any value of x we create a square in 3D. So I'll sweep the square so that we can see how these squares are created, and if we look at all of these squares together, it forms a volume. So what we'll do is we're going to add the area of these squares, infinitely many, that have a thickness of dx. So what does the solid look like? It looks like that. It's a neat shape. We can see how when we go through all the values of x, the squares create that volume. So instead of squares, we can do the same with, for instance, equilateral triangles. So we have the same function, which is a circle or maybe a semicircle. If we look at it in 3D, one equilateral triangle, it doesn't look very much like an equilateral triangle, but let's pretend, is going to be like that. What volume does it generate? A volume like that. And these are volumes with cross sections. So these are the volumes we're going to try to find the volume of. Let's go back to the theory now. Alright, let's get back to our examples. Example 4, cross sections. A pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross section of the pyramid parallel to the base is a square. Find the volume of the pyramid by hand. So here we start at x equals 0, we will go to x equals 3, and each of the cross sections is a square of base x times x. So we're going to apply this formula for the volume. The volume from 0 to 3 of the area times dx is the integral from 0 to 3 of x squared dx, and that is equal to 9. Since this is a pyramid, we could also use a geometric formula, base times height over 3, and we would find 9 as well. So the volume is 9 meters cubed. Example 5, much more like what you will see in actual exercises. A mathematician has a paperweight made so that its base is the shape of the region between the x-axis and one arch of the curve y equals 2 sine x. Each cross-section cut perpendicular to the x-axis is a semicircle whose diameter runs from the x-axis to the curve. Find the volume of the paperweight by hand. So y equals 2 sine x, and each cross-section perpendicular to the x-axis, so like this, has the shape of a semicircle. So I'm going to try to make a drawing in 3D here by pushing the y-axis down. It sort of looks like that. I hope you can see what I tried to do. And these cross sections are like this. So there's semicircles everywhere, and this creates kind of a volume that is quite pointy here and quite pointy over there. So what is the area of one of these semicircles? It's pi r squared over 2, because it's a semicircle. What is the radius? The radius, if you think about it, is half of the diameter. So the diameter of this, the largest of these red semicircles, the diameter is f of x over 2. Sorry, the diameter is f of x, so the radius is f of x over 2, which I wrote here as y over 2. If I substitute y, we get area equals pi times 2 sine x over 2 squared over 2, and this simplifies as pi over 2 times sine squared x. Now we use the formula to find the volume of this paperweight. It's the integral from 0 to pi of the area times dx. The area we saw is pi over 2 times sine squared x. And before we do it by hand, we'll look for the answer with our calculator. You can place the pi over 2 in front since it's a constant, and you get 2.467. So that means, since we had units, the paperweight units were in centimeters, that the paperweight's volume is 2.467 cubic centimeters. This is if you do it with your calculator. I don't think it's so important to be able to do it by hand, but I'll still show you. If we go back to this position, the integral of sine squared x dx, how do we do that? We use a trigonometric identity that is sine squared x is actually equal to 1 minus cosine of 2x over 2. You may have seen it in pre-calc, but maybe not. This is equal to the integral of pi over 4. So it's equal to pi over 4 times the integral from 0 to pi of 1 minus cosine 2x dx, which is much easier to integrate. The integral of 1 is x, the integral of cosine 2x is half sine 2x, and when we substitute, the good thing is we find an exact value. We don't find 2.4, whatever it was. We find the exact value. The volume is pi squared over 4. So all you have to remember, the most important thing is that to find the volume of these cross-section, you're going to integrate a of x times dx. Once you are able to find what the area of the cross-section is, here it was a semicircle, then you're good. So to conclude, we're going to review the objectives. To find the volume of a solid of revolution using the disk method is what we did, for example, in example 1. So piling up disk, we have one disk, but we actually have infinitely many, and it creates a volume. Using the washer method, same idea. We find, in fact, the volume of the whole block, and then we subtract the volume of the smaller part, which is actually a hole. It's like we carved in a hole in our original block. And finally, cross sections, where you will always be given the shape of the cross section. It may be squares, so then you know a of x is maybe x squared. It might be equilateral triangles. Here it's semicircles, but you always need to figure out what the area is in terms of x.